All right, in section 9.4, we're going to look at one particular application of differential equations. And it's particularly the type where we assume or we know that the rate of change in some quantity is proportional to the quantity itself. And again, this isn't too bad of a differential equation to solve, and we can just kind of solve it in general without talking about a particular k. And let's also make this an initial value problem. So let's say that we know that the function at time 0 is equal to some initial amount, which we'll just call y0. Okay, so let's see if we can solve this differential equation. And let's see if it's a separable differential equation. So dy dx equals ky. I think we can multiply both sides by dx and divide both sides by y. And we have separated, and we can now integrate both sides. So this becomes natural log of y. This becomes kx plus c. We'll exponentiate both sides, and we will get y. And again, keep in mind this becomes e to the kx times e to the c, and e to the c is just yet another constant. So we can say this is y equals c e to the kx. And if we go back and say, hey, we do actually have an initial value here, should be that when I plug in 0 for x, I get y0 for y. So let's plug that in. Say y0 is c e to the k times 0. K times 0 is 0, of course. E to the 0 is 1. So we now have a full general solution to this differential equation right here, this initial value problem right here. The solution is always y equals y0 e to the kx. And a couple things are worth pointing out here. It's the y0 is the initial amount. It's just the amount at time 0. And the k is that growth rate, right? It's the k from over here. It's saying, hey, if you've got 100 people and a growth rate of 3%, then the rate of change will be 0.03. So this is the growth rate. Some people call that like the change rate, because you could be growing or you could be decaying. But yeah, this is a general formula, and for the most part, we're not going to need to use differential equations in this section. We're just going to need to use the results of this one differential equation. And if you remember your pre-calculus, this was a formula they just gave to you. Now we can derive it, of course, and that means we can adapt it for slightly different situations. So let's take a look at a few. So this is homework problem 4. I picked all these to be similar to ones that you're doing in your homework. 4 says bacteria grows with a constant relative growth rate. So that means the language there, again, we don't need to write that down, but the language there is the growth rate is constant relative to the actual amount of stuff, actual amount of bacteria in this case. In any case, says after 2 hours there are 600, and after 8 hours the count is 75,000. That means we know the solution to this equation. We know we're looking at a y equals y0 e to the growth rate times x. They said find the initial population, so that means 2 hours before this 600. So they're not actually giving us this initial amount, but we're going to have to figure it out. So we do know we have a couple points we can fill in. After 2 hours, there's 600. So 600 initial amount e to the growth rate 2. And we also know after 8 hours, there's 75,000. So we've got another point here. So there's two equations here, two unknowns. There's multiple ways to solve two equations with two unknowns. You can solve one equation for one and substitute into the other one. A way that actually works out pretty well for exponential equations is rather than maybe subtracting both equations and getting something to cancel, is actually dividing both equations. And I think I actually want to divide these the other way around. So let's look at 75,000 equals y0 e to the k times 8. And let's divide that by 600 equals y0 e to the k times 2. This works because if this is equal to that and that is equal to that, dividing equals by equals still gives you equals. So on the left hand or right hand side, sorry, the y0's cancel. Keep in mind when you divide exponents with the same base, you subtract their exponents. So 8k minus 2k is 6k. On the other side, 75,000 divided by 600. That's what calculator's for. 75,000 divided by 600 is 125. And you may have to think back to your pre-calculus a little bit to remember to take the natural log of both sides next. So the natural log of 125, and the reason we're doing this is natural log and e cancel each other. Equals 6k, so the growth rate is the natural log of 125 divided by 6, and again, that's calculator work. Let's see, we need the natural log of 125. 125 divided by 6. So that's about an 80% growth rate. Let's go 0.8047. Which means that we now have the ability to answer this first question of what's the initial population. We know now that the equation is y equals y0 e to the 0.8047. That is k. This is x right here. And again, we can fill in one of our initial values, like maybe the 2 and 600, and solve for y0. So this is what we know so far. Okay, so filled in the 2. So the initial amount is 600 divided by e to the 0.8047 times 2. And then we can crunch that with the calculator. 600 divided by e to the 0.8047 times 2. Let's see, is that the whole thing? Yep, that was the whole thing. Let's see if we didn't get the 2 in the right place. So let's try that again. 600 divided by e to the parentheses 0.8047 times 2, close parentheses. Okay, that looks a little better. So 120. So initial population's 120. So initial population, part A, 120. We already have part B now, which is to say the full equation that describes the number of bacteria at any given time. Oh, sorry, I see they're using t for the variable. Okay, let's make t. For C, they just want the number of cells after 5 hours, so we can plug 5 in. Let's see, crunch that through. So we've got 120 times e to the 0.8047 times 5. So there's about 6,708. 6,708. Part D asks for the rate of growth after 5 hours, and be a little bit careful here, because they've already told us this thing has a constant relative growth rate, and we know what that is now. It's about 80%, right? It's 0.8047. That's the growth rate relative to the population. So say it'll always be growing at 0.8047 times whatever the population is. But when they, in part D, are asking for the rate of growth after a particular time, they're saying more like, what's the number per hour? And this is what a derivative gives us, right? So we go back to the original y equals 120 e to the 0.8047 t, and say if I want to talk about the growth rate per hour, not the growth rate relative to the size of the population, we need the derivative. And that's a pretty easy derivative. So there's the derivative in general. They want the rate of growth after 5 hours, so we would just put a 5 where this t is. I'm just going to squeeze that in right there. And we grab the calculator and crunch that again. And I'll just skip the calculator work this time and say it crunches out to about 5398. And that's bacteria per hour. The last part here, when will the population reach 200,000? Just set the original equation in part B equal to 200,000. Oops, this is E. And in case it's been a little while since you solved one of these, you start by dividing both sides by 120. And take the natural log of both sides. Again, on the right-hand side, E and natural log cancel, and you get 0.8047 t equals this stuff. And divide both sides by 0.8047. And you get t is the natural log of 200,000 divided by 120. All that divided by 0.8047. And again, that's definitely calculator work at this point. And that works out to about 9.2 hours. All right, so that was just number 4. Again, a lot of sort of pre-calculus, logarithm, number crunching involved. We should take a look at a couple more, and then we will be done.